A team of researchers at IMEC has recently found the trick. They printed a pattern on the chip with a product that the brain cells love to eat. While consuming the product, the cells get stuck to the right spot and their tentacles are guided by the pattern. This way, the whole network of brain cells can be entirely controlled. Dr. DeMars, for instance, tries to communicate with his brain dishes and teach them several tasks.
So each of these dishes contains about 20,000 or so neurons, which are firing away as we speak. So each one's an individual network, and they'll fire spontaneously. We take living rat neurons, and they will rapidly form a neural network. And we have this grid of electrodes underneath the surface of these living neurons, and we can listen to the conversation among the neurons. And we can also stimulate activity within that network. We can send in different patterns of stimulation and look at how the network changes as a result of those stimulations.
What he does is to teach his brain dishes how to control an airplane.
The network can essentially fly the aircraft in a pretty optimal way. So it won't overcorrect too much, and it'll be able to stabilize it in a wide variety of conditions. I think I've programmed like a 50-knot crosswind into this one. It was what it looks like. You can see it, the aircraft, when it hits one of these crosswinds, how it begins to oscillate. Each dish has a characteristic, so you can learn to recognize one dish from another dish. They're demanding, though. You have to feed them once a week.
The paper we are going to cover today is one of the more important things that happened in AI research lately. In the last few years, we have seen Deepmind's AI defeat the best Go players in the world, and after OpenAI's venture in the game of Dota 2, Deepmind embarked on a journey to defeat pro players in Starcraft 2, a real-time strategy game. This is a game that requires a great deal of mechanical skill, split-second decision-making, and we have imperfect information as we only see what our units can see. A nightmare situation for any AI. TLO, a professional StarCraft 2 player, noted it indeed felt very much like playing another human player. This new version can now play all three races, and here you see its MMR ratings, a number that describes the skill level of the AI, and for non-experts, win percentages for each individual race. As you see, it is still the best with Protoss, however, all three races are well over the 99% win rate mark. Absolutely amazing. In this version, there is also more emphasis on self-play, and the goal is to create a learning algorithm that is able to learn how to play really well by playing against previous versions of itself millions and millions of times. This is, again, one of those curious cases where the agents train against themselves in a simulated world, and then, when the final AI was deployed on the official game servers, it played against human players for the very first time. So, how did that go? In my opinion, given the difficulty and the vast search space we have in StarCraft 2, creating a self-learning AI that has the skills of an amateur player is absolutely incredible. But that's not what happened. Hold on to your papers, because it quickly reached Grandmaster level with all three races and ranked above 99.8% of the officially ranked human players. Bravo, Deepmind. Stunning work. In these matches, I love the fact that so many times it makes so many plays that we consider to be very poor, and somehow, overall, it still plays outrageously well. It has unit compositions that nobody in their right minds would play. It is kind of like a drunken Kung Fu master, but in StarCraft 2. Love it. As amazing as it sounds, Deepmind wasn't just looking to spend millions and millions of dollars on research just to play video games. The building blocks of Alpha Star are meant to be reasonably general, which means that parts of this AI can be reused for other things. For instance, Demis Hassabis mentioned weather prediction and climate modeling as examples.